In this section, we'll examine in greater detail the different currents underlying the action potential. Here's our action potential again. We have the initial depolarization, which brings us to threshold. There's a rapid spike in voltage called the rising phase, followed by a slower decrease called the falling phase. Finally, we arrive back at the resting potential and in fact undershoot it slightly. The entire action potential only spans a few milliseconds. Voltage-gated ion channels are critical to the formation of the action potential, so let's look at them in greater detail. We'll again start with the cell membrane. So that we can perturb the cell, we're going to place a stimulator electrode inside the cell. We'll also give you a recording electrode. It's important to know what the stimulator actually does. It injects charges into the cell by applying a small current. But it's the membrane potential that actually changes the conductance of the voltage-gated ion channels that we talked about earlier. The membrane potential doesn't immediately change in response to a new current across the membrane because of the membrane capacitance, a topic we covered in a previous lesson. Let's see what that actually looks like. Our changing current is a square wave. If we look at the recording electrode, we have a delayed change in the membrane potential. We're now going to introduce the voltage-gated sodium channel into our membrane. At rest, the majority of channels are in the closed state, like this one shown here. Remember that the voltage-gated sodium channel has a higher probability of being open when the membrane potential is more positive. We're only showing you one channel here in the membrane, but the continuous change in the conductance comes from the effect of thousands of channels together. This plot here shows the overall conductance of sodium in the membrane as a function of time. As we use the stimulator electrode to depolarize the membrane, more channels open. More open channels means a greater sodium conductivity, and consequently a greater sodium current. When we reach threshold, which typically occurs somewhere around -55 millivolts, there's a dramatic increase in the sodium conductance. For now, let's think of it as a point of no return. An action potential will be fired once we cross some threshold voltage. This increase in sodium conductance causes a rapid depolarization of the membrane as sodium rushes down its concentration gradient into the cell. This causes the rising phase of the action potential.